Hello. Today, we finish up our two-part series on the adjoint of a linear operator. First, let's review some concepts from before. Let's let V be a vector space over either the real numbers or the complex numbers, and let's fix an inner product. We have two statements. For any vector y in our vector space V, let's let G be that map from V to the scalars f that sends a vector x to the inner product of x with y. Then G is a linear transformation. Conversely, let G be a linear transformation from our vector space V to the scalars f. Then there exists a unique y in V such that G of x is the inner product of x and y for all x in V. Next, let T be a linear transformation from V to itself. Then there exists a unique linear transformation T star, also from V to itself, such that the inner product of T of x and y is equal to the inner product of x and T star of y, for all vectors x and y. We make two comments about all of this. First, the first statement states that linear transformations G from the vector space V to the scalars are in one-to-one correspondence with vectors y and v. Second, we'll use the second property to write down a definition. Say that T is a linear transformation from V to itself. The linear transformation T star is called the adjoint of T. Let's go over an example. Let's let V be the two-dimensional vector space over the complex numbers, and let's consider the standard inner product as you see on your screen. Say that we have a linear transformation T from V to itself in terms of a matrix A, B, C, D. We can then compute the inner product of T of x and y as a sum x1 times A y1 conjugate plus C y2 conjugate plus x2 times B y1 conjugate plus D y2 conjugate. Using this, let's write down a second linear transformation U from V to itself in terms of the matrix A conjugate, C conjugate, B conjugate, and D conjugate. We then find the exact same expression as above for the inner product of x with U of y. This means that the adjoint of T is our linear transformation U, and moreover, the matrix associated to the adjoint of T, namely A, B, C, D star, is equal to the matrix corresponding to U, namely A conjugate, C conjugate, B conjugate, and D conjugate. We're going to come back and discuss this expression a bit more today. In fact, this actually motivates the concept of the adjoint of a matrix. Let's consider the following result, which is the main result for the day. As before, say that V is a vector space over either the real numbers or the complex numbers and fix an inner product. Let's let T and U be two linear transformations from V to itself, and let C be a scalar. Fix an orthonormal basis beta for V. We'll denote A as the matrix representation of T with respect to beta, so that A star, namely the matrix representation of the adjoint of T with respect to beta, is the complex conjugate of the transpose of A. We also have three properties. First, the adjoint of CT plus U is equal to C conjugate times the adjoint of T plus the adjoint of U. Second, the adjoint of the composition of T with U is equal to the adjoint of U composed with the adjoint of T. And finally, the adjoint of T is just T itself. Before we try to prove this proposition, let's recall some definitions. Say that A is an n by n matrix. That n by n matrix A star, which is the complex conjugate of the transpose of A, is called the adjoint of A. However, don't confuse this with what we define as the classical adjoint of A, that is the adjugate of A. It is that n by n matrix whose entries ij are -1 to the I plus j times the determinant of A j I tilde, where A I j tilde is that n minus 1 by n minus 1 matrix obtained from A by deleting the ith row and the jth column. Here's an example when n is equal to 2. Let's consider the matrix A, which we have as the entries A, B, C, and D. This means that the adjoint, namely the complex conjugate of the transpose, is that 2 by 2 matrix A conjugate, C conjugate, B conjugate, and D conjugate. On the other hand, the classical adjoint, that is the adjugate of A, is that 2 by 2 matrix with entries D minus C minus B and A. Note that the adjoint and the classical adjoint in general are very different matrices. Let's consider an example. Say that V is the collection of n-dimensional vectors. Recall that the standard inner product is the sum that you see here on your screen, and we claim that this can actually be expressed in terms of the adjoint. Namely, the standard inner product is the sum x1 times y1 conjugate plus x2 times y2 conjugate, and so forth. This sum, of course, is a scalar. If we consider our vector y, which is an n-dimensional column vector, its adjoint will be an n-dimensional row vector. Therefore, we can write the scalar, namely the inner product of x and y, as the product of the matrices y star times x. It's easy to see that the standard basis, in terms of the standard basis vectors, e1, e2 through e sub n, is an orthonormal basis with respect to this standard inner product. Let's make the following observation. With respect to the standard basis, we see that the matrix representation of left multiplication by A is just the same as the matrix A itself. Now let's consider the adjoint of this left multiplication by A. According to the previous theorem, since beta is an orthonormal basis, we see that this is the same as the adjoint of A, namely A star. However, this is also the same as left multiplication by the adjoint, at least the matrix representation thereof. So we've actually shown now that the adjoint of left multiplication by A is left multiplication by the adjoint of A. This explains why we can use the word adjoint with the linear transformation somewhat interchangeably with adjoint of a matrix. We do want to caution, though, that this only works if you have an orthonormal basis with respect to a given inner product. Now let's go ahead and prove the theorem. We'd like to prove the first statement, so let's say that beta is an orthonormal basis for V. We can express any vector y as a linear combination of elements from this basis, but the point is that since we have an orthonormal basis, we actually know a lot about these scalars corresponding to the linear transformation. Let's denote capital A as the matrix representation of T with respect to this basis beta. From the way that we've defined things, we can express now the image under T of all of the elements in the basis as a linear combination of elements from this same basis. Simply put, if we let y be T of u sub j, then we have the system that you see here on your screen. Now recall the way that we've defined the matrix representation. We easily see that the entries of our matrix A, namely Aij, are just the inner products of T of uj and ui. Similarly, let's let B be the matrix representation with respect to the adjoint T star. Then this means that all of our entries Bij can be written as the inner products of T star with uj and ui. Now, since our inner product is symmetric, we can write this in terms of the complex conjugate of the inner product of ui and T star of uj. Now we use the fact that we have an adjoint, so we can slide T to the left, and this is, of course, the complex conjugate of the inner product of T of ui and uj. But looking at this is really just the complex conjugate of Aj, which of course is the same thing as saying that B is the complex conjugate of the transpose of A. This shows the first statement. Let's now show the second statement. Recall that we have three properties we'd like to show are true. For all vectors x and y in our vector space V, we have the following. Let's take a look at the inner product of x and ct plus u star of y. Since we have the adjoint, we can slide ct plus u to the left-hand side, then use the fact that we have a linear transformation to then express this now as a linear combination of inner products. Now we can slide t and u to the right-hand side by looking at their adjoints, and then combine everything back together again, since again our inner product is linear. But now we see, putting all of this together, that indeed ct plus u adjoint is equal to C conjugate times T adjoint plus U adjoint. Let's prove the second of the three properties. Similarly, for all vectors x and y and v, we have the following. We can take a look at the inner product of x with the adjoint of t circle u and y. Since we have the adjoint, we can slide things over to the left. And now we realize that the composition just means t of the vector u of x and y. We can slide t over to the right by looking at the adjoint, and then slide u over to the right by looking at the adjoint. Now on the right, we realize that this is just the composition of u adjoint and t adjoint. So putting all of this together, we do see that the adjoint of t circle u is the adjoint of u with the adjoint of t. Finally, we show the last property. Again, for all x and y and v, we have the following. We can take a look at the inner product of x and t of y, which is the complex conjugate of t of y and x. Now we can slide t over to the right by looking at the adjoint, and then we can use the fact that since we have the complex conjugate, we can simply use the symmetric property to move things around. This is the inner product of t star of x and y. Again, let's move t star to the right by using the adjoints. And now staring at this, we see indeed that t is equal to the adjoint of t, which completes the proof. Thanks very much for watching.